Hello and good afternoon friends, welcome to CECA Reset Live lecture. In previous section of ours, that is in the previous lecture of ours, that is yesterday, we talked about quantum chemistry. We tried to learn about various aspects of the quantum chemistry as well as we, with the help of various examples, try to understand the various concepts and this very concept. And yesterday we talked a lot on it, and for this today also we have with us in our studios Professor Rita Kakkar. She is professor in Delhi University in the chemistry department. Again, she is with us, and I wholeheartedly welcome our guest, Professor Rita Kakkar. Dr. Kakkar, we tried to understand about this very topic and we left with the postulates, and I would like you to please introduce once again with the postulate portion.
Thank you. Good afternoon, viewers. We'll again begin with the postulates, because if you remember that while we were doing the postulates, there were some questions put up. I'll answer those questions. I had answered, but there were some graphics that I wanted to show, but I'll do that after I have done the postulates and introduce the Schrodinger equation, because otherwise it will be difficult to understand those. Now, if you remember, we are at the postulates of quantum mechanics, and I had explained what a postulate is. That it is a statement which is assumed to be true without giving any proof, and the truth of it lies in the fact that nobody has ever proved it wrong. And quantum mechanics, the postulates have never been proved wrong. The first postulate, if you remember, was concerned with the wave function, and we said that the wave function is a function of the coordinates of the atom or whatever system you are looking at, as well as the time. Depending upon the number of particles that are present, that many coordinates will be there, and for every particle there will be 3 coordinates, because we are working in 3 dimensions. So there will be 3n direction and the time. So the wave function is a function of a large number of coordinates. It's a vector quantity, and we said that for it to represent what we want it to, because the wave function contains all the information about the system, but the wave function by itself does not have any meaning. Born told us that the meaning of the wave function is that its square represents the probability of finding it at a particular position, represented by whatever R1, R2, etc. at a particular time t. So if it has to represent a probability, we need certain conditions. It should be well behaved. That means that it should satisfy certain conditions, and these conditions were that it should be continuous, because if it is discontinuous, it means that the probability suddenly changes from 0 to say very high between 2 points. It should be square integrable, and the reason for that is that if its square represents the probability, the total probability over all volume should equal to 1, and this total probability can be obtained by integrating. So if you are not able to integrate that function, you will not be able to represent it as a probability. It should be single valued, because for a particular position you cannot have more than one probability of finding the particle at that position. So these were the conditions, and then we will see that it should also obey the boundary conditions, and when we do the particle in a box problem, you will realize what I mean by that. And then I had explained what we meant by the volume element and so on, and I think we will quickly go over that. And then I had shown a graphic where we had seen that the probability itself can be positive, or the wave function itself can be positive or negative, but its square can never be negative, and because it represents a probability, you cannot have a negative probability anywhere. It can also be complex valued, in which case we make it real by multiplying by its complex conjugate, which means that wherever we have iota, the imaginary number, the square root of -1, we replace it by minus iota, so that iota multiplied by minus iota will give us 1. Now, we had talked about the weirdness of the first postulate. We said that instead of being able to pinpoint that the particle is here, we can only talk in terms of probability. We can say that the probability is maximum at the center of the this ellipse that we have drawn, but we cannot go beyond that. We cannot say that the particle is certainly there. there is a probability everywhere, even at very large distances from that center. So this is something really weird, because we are used to saying the chair is lying here, the table is here. We cannot say that it has a probability of being here, but when we are working with small particles, this is how we represent the position of the probability. We can only talk about its position. We also said that since a particle can be represented as a wave, and a wave can be written as a superposition, that means as a linear combination of different waves which behave similarly. If we are talking about an elephant, and we know that it can have two colors, there are no multicolored elephants, but as an example, just a hypothetical example, I am taking, suppose there were two elephants, they could be grey, the usual ones that you see, or they could be multicolored. What a quantum elephant can have, that in quantum mechanics terms we will say that it can have two states, it can have either have a grey state or a multicolored state, and as a total we can say that it is a superposition of those two states. So the wave function is represented as the wave function for the grey elephant plus the wave function for the multicolored elephant. And now I talk about the paradox of the Schrodinger cat. This is a thought experiment where we assume that there is a cat in a box where there is a poison filled glass bottle, and if the cat knocks off that bottle, and it has to take the poison and it dies. Now until you open the box, you don't know what is happening inside. So according to quantum mechanics, we will represent that there are two states of the cat. It can be dead or it can be alive, so that in quantum mechanics terms we can say that it is equal to half probability. Remember that 1 by square root 2 will get squared, so that means that there is half probability that the cat is dead and half probability that it is alive, because the square of the wave function 1 by square root of 2 will become half. So this is what are the strange events that happen. And now I have a quote from Einstein himself, the one who was in the middle of all this when it was happening. He refused to believe Born's interpretation, and he said God does not play dice with the universe. You know what, we've shown the dice here, that it is not a game that God is playing, that sometimes he is saying the probability is this much somewhere and the probability is something somewhere else. So this is what one of the great scientists of that time, Einstein, had to say about quantum mechanics, although he was one of the people who brought in quantum mechanics. Now we move on to postulate 2, that it says that the motion of a non-relativistic particle, we will not bother about the non-relativistic particle definition, but we will say that the motion is governed by the Schrodinger equation, and this equation can either be written as a time dependent. The actual Schrodinger equation is the first one that I have written, iota h cross d by dt. You will see that this h cross, Planck's constant divided by 2 pi, is a very fundamental constant, keeps on cropping up everywhere. Psi t is equal to the Hamiltonian operating on psi t. I will explain what we mean by the operator, the symbol, the hat kind of symbol before above h. I will explain all these terms in the next few slides, but this is the complete Schrodinger equation. It can be shown that if the wave function does not depend upon time, that means it is time independent. It is an isolated system which is not being acted upon by external forces, so it's not changing its energy with respect to time. In that case, this can be written as the familiar Schrodinger equation, h psi is equal to E psi, and in molecules we normally write it as minus h cross square by 2m, where mass is represented by m, d2 by dx square, it's a differential equation, the second derivative, plus the potential energy operator V, when it operates on psi gives you the energy, that the total energy is the sum of the kinetic and potential energies, and this when it operates on the wave function it gives you the energy. I am telling you about this postulate at this time because we have to say how did we get this wave function. By solving the Schrodinger equation we are able to derive the wave function for various systems, but like I said yesterday, I will emphasize that quantum mechanics is able to give you exact solutions only for a handful of cases. One is a particle in a 1D box, 2D box or a 3D box. The second is the rigid rotator, the hydrogen atom, and then you have the even the helium atom cannot be solved exactly by quantum mechanics. Then we have the harmonic oscillator problem that you can easily solve completely using Schrodinger equation. The solutions may be very complicated, but we can solve these. And then we have the rigid rotator problem, which is a subset of the hydrogen atom problem that we can solve. Again, I am saying they are very complicated solutions and we will not be able to complete them in the next lecture also. I will only concentrate on the particle in a box problem. Now, what are the interesting facts about the Schrodinger equation? The moment you use the Schrodinger equation, you are talking about a wave function. That means you are treating the particle as a wave, but since you are also talking about the mass of the particle, you are also treating as a particle. So, Schrodinger was the first one to realize the dual character, and he talked about a wave equation which was applicable to particles. Now, it is a wave equation whose solutions display interference effects. Because it is a wave equation, it behaves like a wave and it can show interference effects. It implies that time evolution is unitary and therefore reversible. It is very difficult to solve for large systems. That is, when there are more than 3 particles, it is almost impossible to solve it. Then this is the Schrodinger equation. Schrodinger is one of the best known scientists. In fact, he is the one who probably I will not call it a derivation, but who wrote the Schrodinger equation, and today it is being used in so many places that it is for all the new kinds of systems that we are coming across, the semiconductors and so on, we have to use the Schrodinger equation. And it contains both wave and particle terms. It cannot be derived from any principle, and because it is a fundamental law of nature. You can only judge that it is correct because nobody has proved it wrong, because whatever we derive using the Schrodinger equation is correct, is able to explain the behavior of whatever particle you are trying to solve. Now, I am talking about an argument that must have gone around in Schrodinger's mind when he derived this equation, that the wave equation can be written as del square psi. This is del square is an operator in 3 dimensions, which is d2 by dx square, it is a second derivative, plus d2 by dy square in all the 3 dimensions, plus d2 by dz square. It is called the del square operator, and minus 1 by c square. C is the speed of light, which you remember is 3 into 10 raised to the power of 8 meters per second, and that when it is multiplied by d2 psi by dt square, we take the derivative with respect to time, it is equal to 0. Now, when you write down the wave equation, when it is propagating in the x direction, you usually express it as a complex exponential 2 pi iota x by lambda. Lambda is the wavelength of the wave, minus nu is the frequency of the wave, and t is the time. So, if you combine these two and you apply the Planck and de Broglie formula to these, you get the wave equation exponential iota into px, where p is the momentum, x is the position, minus et, where e is the energy and t is the time, divided by h cross, and h cross as usual is the Dirac constant or the Planck constant divided by 2 pi. Then what he must have done is that he must have substituted that the energy contains 2 terms. It has a kinetic energy which can be written as half mv square, and the momentum is equal to p is equal to mv, and so you can write down p square by 2m for the kinetic energy, and then he by putting it in the Schrodinger equation, in the wave equation, he got this equation iota h cross d psi by dt is equal to e psi, or minus iota h cross d psi by dx is equal to p psi, or p square psi is equal to minus h cross square d2 psi by dx square, and the energy is, the kinetic energy is just p square by 2m, and using that he was able to get Schrodinger equation that I have already told you about, that it is equal to minus h cross square by 2m d2 by dx square plus Vx, where V is the potential energy and it is a function also of the position. So, this can be easily extended to 3 dimensions, and when you extend to 3 dimensions, instead of d2 by dx square, you have the del square operator, because that is for 3 directions, and you have the time independent Schrodinger equation that is usually used in quantum mechanics. It is only when we are studying spectroscopy or when there is time evolution of the function that we work with the time dependent Schrodinger equation. It is the last equation that we will be bothering about. Now, it may sound very complicated, but once you start using that, you will understand that the Schrodinger equation was derived using classical equations that they had at that time, but inserting the wave equation by recognizing that particles both have wave character and the particle character. And what is this weird thing about this postulate? See, when you have a classical particle, there is a mouse and you ask it to go through this maze, there is only one way that it can go. But according to quantum mechanics, the Schrodinger equation tells you it is a wave, it can use any one of these, it is a quantum mouse, it can go anywhere in these directions, and there is no non-zero probability anywhere. Now, I will try to explain, we will discuss the operators later on, because already we have come across the Hamiltonian operator when we wrote down H with a hat over it. Actually, it is called a caret symbol. The moment we used it, we were talking about operators. I will try to explain the operators, but before that I will split the third postulate into 2 parts. It says that I can safely say now that the Hamiltonian that we wrote just now was the energy operator. It was the operator for the energy. We will understand this. What the third postulate says is that every observable is represented by a linear Hermitian operator. First thing, what is an observable? It is anything that you can observe. It could be the velocity, it could be the momentum, it could be the energy, it could be the angular momentum. Any property that can be observed is called an observable. So, for what the third postulate tells us is that for every observable in quantum mechanics, there is a linear Hermitian operator. We will explain each one of these terms, starting with operator. What is an operator? It is like, it tells whatever is after that, what to do to that. There is a function which is followed by the operator. You have an operator. When it operates on a function, it gives you another function. So, operator tells you what to do with the function. One operator could be the differential operator, dy dx, and you know that when it operates on the exponential alpha x function, that means e raised to the power of alpha x, it gives you alpha multiplied by e raised to the power of alpha x. You started with a function e raised to the power of alpha x, and you operated with the differential operator dy dx, and you got alpha multiplied by e raised to the power of alpha x. So, your dy dx is the operator, exponential alpha x is the function, and when it operates on the function, it gives you another function which is alpha raised to the power of alpha into e raised to the power of alpha x. So, an operator is a generalization of the concept of a function, whereas a function is a rule for turning one number into another. Function, for example, 2 into 5, that is, it tells you how to convert 2 into 10, you multiply by 5. Similarly, in this case, if you have an A operator, it operates on a function f, it gives you another function, this time g. It could be a different function, or you could get back your old function. The Laplacian operator, the one that we had used, the del square, that also is an operator because it tells you what to do with the function that follows it. The operator by itself does not have any meaning, but when you write a function after that, it gains some meaning. We usually indicate that an object is an operator by placing a hat over it. That is, for example, A is an operator, you put a hat over it to tell that it is an operator. Multiplication is also an operator. So, anything that tells you what to do with a function that follows it is an operator. What the third postulate told us is that for every observable you can get an operator. We will talk about how we get the operator, but before that we said it should be linear and it should be Hermitian. Now, the definition of a linear operator is that suppose it operates on a linear combination of functions. What do we mean by linear combination? suppose you have two functions f1 and f2, you multiply each one of them by a constant. For example, you have a function x and another function x square. 2x plus 3x square is a linear combination because you are multiplying it by a constant, one function, and the other one by 3. So this is a linear combination of functions. What the linear operator does is that it is the same as if you operate on each one of them individually and then you add. One good example of this operator is d by dx, because if you have to operate with d by dx on a function x plus x square, you will first operate on x and then with x square and then add up. That is a linear operator. What it tells us is that all operators in quantum mechanics are linear operators. So if they operate on a linear combination of functions, you can easily do that. It first operates on one function, the constant can be taken out because the operator does not do anything to a function and to a constant, and then you only operate on the function. The operators involved may or may not be differential operators. That means that they may or may not involve differentiating the wave function. I have been taking an example of differential operator, but as I said, even multiplication is an operator. Anything that tells you what to do with a function is an operator. You will come across many operators which involve multiplication alone. We also said that the operator should be linear Hermitian operator. I have told you what an operator means. I have also told you what linear means. Now we come to the definition of Hermitian operator. Remember that our functions are complex also, can also be complex. So what it tells you is the integral at the top, that if you take the function I, you take its complex conjugate and you multiply it by an some operator O which operates on fj, and then you integrate over all space. This is one dimensional space. It is the same as if you had taken the second operator outside the operation and operated with the complex conjugate of the operator. A star means that it is a complex conjugate, where, as I explained before, everywhere there is an iota, you have to replace by minus iota. Your operators can also be imaginary. For example, iota d by dx is an operator. So wherever I is there, you can change it to minus iota to get its complex conjugate. It is the same as if you operate on the complex conjugate of the function I with the complex conjugate of the operator. Now we will not go into any kind of derivation of this, but why do we need Hermitian operators? We need Hermitian operators because there is a theorem which says that Hermitian operators have always real eigenvalues, and I have not told you what eigenvalues are. We will talk about them in the next few slides. So the examples of Hermitian operators are the d by dx operator that we have been talking about for so long is not a Hermitian operator. We will not find any operator d by dx in quantum mechanics, but it's if you write an iota before that or a minus iota before that, it becomes Hermitian, and that is why I told you that our operators can be complex also. D2 by dx square operator, if you take the second differentiation, that is a Hermitian operator, and you will come across this operator when you are doing the in Schrodinger equation. The kinetic energy operator involves d2 by dx square. So how do you identify the operators? We identify the operators in a very simple way. I mean, you may be wondering, I want to write down the operator for the angular momentum. How do I write it down? It is very simple. Just remember two operators. Remember, I told you that there are two complex conjugates. There are two conjugate variables. One is the position and one is the momentum in the same direction. Suppose we are talking about the x dimension. The operator for x is simply x, that means multiplication by x, but for the momentum the operator is minus iota h cross d by dx. You write down and in 3 dimensions I have written on the right. We will only worry about the first dimension, because once you understood that, it becomes easy. Then the second step is you only have to remember the operators for the position and for the momentum, and if you are working in 3 dimensions, px becomes py and dy dx becomes d by dy and so on. It is very simple. The y operator becomes multiplication by y and z operator becomes multiplication by z. Then you write down the classical expression for that particular quantity in terms of the momentum and the position, and wherever you have the momentum, replace it by its operator, and wherever you have the position, replace it by the corresponding operator. You will see examples here. Suppose you want the kinetic energy in the x direction. As I just told you that half mv square can easily be written as p square by 2m, and since we are working in one dimension only, that it is px square by 2m, and the operator px square by 2m can now be replaced, px everywhere can be replaced by minus iota h cross d by dx, and when you take the square it becomes d2 by dx square. And similarly you have other examples also. You can talk about the angular momentum where r into p becomes you can write it down as a vector quantity, right, I, j, k for the unit vectors, and you can write down x, y, z for r, and for p, px, py, pz, you can get the 3 components of the angular momentum in terms of the position and in terms of the momentum. And once you have got that, you can easily find out the 3 components of the angular momentum, and you can find out what are the corresponding eigenvalues and eigenvectors that we'll talk about. May I have the slides?
Please show the slide.
Actually, this is wrong.
We are talking about this quantum chemistry, and I hope all the students or viewers who are watching us are able to get into it, and we are can we proceed further, ma'am, without the slide, if it is possible?
I think it's not possible with the science subject. That
it's not possible, but the question here is how we are able to differentiate if we with this quantum chemistry, if we talk about how it is different from the other forms of chemistry.
I've already said that in classical mechanics, you can you know everything about the system. You can say that it is at a particular position. You can talk about it is not associated with a wave. In quantum mechanics, every particle is associated with a wave. So once you have a wave, you can only talk about probabilities. You cannot talk about anything with certainty. You cannot say that the particle is here. You can only talk in terms of the probabilities.
We can only talk in the terms of the probability. And as you were telling about Einstein, we have a call from UP before we continue our lecture further. I think we should take the call. Hello.
Hello.
Yes, please ask your question.
Oh, what is the solution of Schrodinger wave equation?
What is the?
Please speak loudly.
What is the
solution of Schrodinger wave equation? How do we find it?
How do we find it? You told about this Schrodinger.
See, I said that everything in quantum mechanics does not have any derivation. These are all postulates, and these postulates do not have any derivation. You just have to accept it as such, and the only proof that all this is correct is because it has been proved correct. Whatever we predict using Schrodinger equation is perfectly correct. I have given you the argument that must have gone in Schrodinger's mind when he wrote this equation. He took the wave equation, inserted the particle character from de Broglie's equation and the wave equation, and then he arrived at some kind of Schrodinger wave equation. But there is no derivation. If some book tells you there is a derivation, it is absolutely wrong. You only have to accept it as such. The postulates have to be accepted as such, and you should not be asked to do a derivation of Schrodinger equation.
I hope our caller might have got his answer, and it is a humble request to all the students and the viewers who are watching us. Please speak your question loudly so that it is easier for ma'am to interpret your answer well. And answer your question very well. So ma'am, we were talking about this quantum mechanics only, and I would like to ask about the Einstein. As you said in the previous lecture also, how he quoted that it is difficult to understand the quantum mechanics, or if we talk about this mechanics in particular, but how it was easier for Einstein to go along with this particular quantum mechanics.
You see, all this happened very, very quickly. Till 19th century, everybody, they were in fact very, very satisfied that they thought they had learnt everything. There was no science left that they needed to find out. They thought that the only things that required any interpretation was maybe the speed of light. You would want it to a better precision or something like that. But then they were jolted out because there were certain things they were not able to explain using the existing theories. And so they had to Planck himself, who I would say was the first person who talked about something like quantization. It is something like this. You see, in classical theory, you can go up the, like a ramp. You can continuously keep on changing your potential energy by even small amounts depending upon the steps you take. But in quantum mechanics, it is like you are going one step at a time. You can change your height from this to this, but nothing in between, because there is no step in between. It is something like that. But then those who were used to continuous energies and suddenly they are told no, the energy levels have to be either this or this, it is difficult when you come across something out of this.
I think we have a caller waiting for us all the way from Uttar Pradesh. Hello.
Hello, मैं क्वेश्चन पूछ रहा था. What is the relation between quantum mechanics and classical mechanics?
Want to ask the difference?
Similarities?
See, I in yesterday's lecture itself, I said classical mechanics. In fact, everything is governed by quantum mechanics. So that is a myth. You should not feel that only the small particles are governed by quantum mechanics. Everything is governed by quantum mechanics. The only thing is that the quantum effects are not, you are not able to see the quantum effects when you have large particles, because in fact, if I am able to do the particle in a box, I will show that as the box becomes large, as the mass of the particle in the box becomes large, the energy levels become almost continuous. So what you see is that almost continuous energy levels, and that is why when you are looking at the trajectory of a ball or any other equipment like that, you will not be able to see the quantum effects. You will not see that it is just jumping from one point to this point only and not stopping. You will see a very smooth kind of change in its energy. Now classical mechanics is very easy because you only use Newton's laws and so on. You don't have to take the all the kind of interactions between the different particles and try to solve a differential equation and so on. So that is why when you are working with particles which are of large size, which you can see and so on, macroscopic objects, you will only apply classical mechanics. But when you come down to the electron, in that case you will have to apply quantum mechanics, and it is complicated, but you have to apply it because classical mechanics will not work.
We have another caller from Haryana. I think the call has been disconnected. Yes ma'am, you were elaborating more on the classical and the quantum mechanics. Do we have another more thing to learn about this quantum and classical mechanics while differentiating?
I mean, it is see, you have to see at what point classical mechanics and quantum mechanics merge. There is a correspondence principle which tells you that in the limit of very high quantum numbers, I will tell when we go to very high quantum numbers, classical mechanics and quantum mechanics gives you the same results. So this is what one has to know in what, like nanoscale. Nano is between an atom and bulk. Bulk is something classical. So when you are in the nano regime, neither quantum mechanics nor classical mechanics will work. So you have to be very careful how to interpret it. So we were talking about the operators, and we had come to the definition of Hermitian operators, and I had also talked about the identifying the operators, and we had said that the kinetic energy operator can be simply written as minus, you write it down in terms of the momentum and the mass. Everything has to be written in terms of the momentum and the position. Here the mass of course is a constant, so you can retain it, and that the kinetic energy operator is then the square of the
Sorry
momentum.
to interrupt you ma'am, there is a caller waiting for us all the way from Haryana. Hello.
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 Yes, please ask your question.
How do we apply Hermitian operator in Schrodinger wave?
See, you need not check whether the operator is Hermitian or not. All quantum mechanical operators that you derive, I am actually doing this only, how you derive the operators, they will turn out to be Hermitian. But as an exercise, we do ask our students to find out whether an operator is Hermitian or not, and you will find these derivations in books to prove that iota, if you multiply d by dx by iota, it becomes Hermitian, but d by dx itself is not Hermitian. And similarly, d2 by dx square is a Hermitian operator. See, I am actually doing this only. The kinetic energy operator, I said, is px square by 2m. So, you write down what is the square of an operator. You operate twice with that operator, once and then another time. So, that means you are taking the square of the operator. You are taking 1 by 2m multiplied by minus iota h cross d by dx. When you take the square, minus iota square becomes iota square, minus iota whole square becomes iota square, and iota square is equal to minus 1. So, you get a minus here, h cross square by 2m d2 by dx square. That means you operate with the second derivative, and I have already told you that the second derivative operator is Hermitian. Automatically they will turn out to be Hermitian if you use the method that I have told you, that you write down the classical expression for whatever you are trying to derive, replace x, y and z by the operators x, y, z, which means multiplication by x or y or z, replace px, py, pz by the corresponding operators, which is minus iota h cross d by dx. This is a Hermitian operator because you multiplied d by dx by iota. Automatically your operator will turn out to be a Hermitian operator. The energy operator is the kinetic energy plus the potential energy. Look, we are talking about a wave equation, so we are realizing the particles are waves, but we are also realizing that these waves have energy, which is given by the total of the kinetic energy plus the potential energy. And whenever you are trying to do a system, the kinetic energy operator will always be minus h cross square by 2m d2 by dx square in one dimension, del square if it is in 3 dimensions. All you have to write is the expression for the potential energy in terms of x, y and z. Now, the angular momentum operator is a vector operator, and it is the vector cross multiplication of r, which is position by p, and this leads to minus iota h cross r cross multiplication by delta, and from this you can get all the 3 components of the angular momentum operator. See, one need not bother about checking whether an operator has turned out to be Hermitian or not. If you use this method, it will be Hermitian. But why do we need Hermitian operators? The reason is that, remember, this operator represents something about an observable. Your observables cannot be imaginary. Hermitian operator ensures that the observable quantity is real. I will come to that soon. Some of the quantum mechanical operators are, I said, that px we have already talked about, the Hamiltonian we have talked about that, and we have the eigenvalue equation SI is equal to E psi. I am using new words and I am coming to those new words. And this is some of the quantum mechanical operators. You will easily find them in books. All of them are Hermitian operators. Okay. I actually, as a teacher of quantum mechanics, I find the students are more worried about the mathematics involved. I concentrate more on the concepts. So, although you will find out, how to prove something is Hermitian, you will find out theorems which prove.
We'll discuss on it, ma'am. Before that, we have a caller from Haryana. Hello. Hello. Yes, please ask your question.
Kinetic energy. What is kinetic energy?
What is kinetic energy?
It is just the classical kinetic energy that you have learnt about in school. When a ball is moving with velocity v, it has a mass m. The kinetic energy is equal to half mv square. It is the energy of motion. So, every particle has a kinetic energy when it is moving, and it has a potential energy. For example, potential energy is given by mgh when a particle is at a height h, then because it is against the gravitational force, it has a mass m, its potential energy is given by mgh. Its kinetic energy, if it is moving, is given by half mv square. This is what you might have learnt in school in physics in 6th or 7th. The kinetic energy is always given by half mv square, but in quantum mechanics we use the same expression. Realize this, that classical mechanics and quantum mechanics, the expressions are the same. The only thing is that you replace the expression by its corresponding operator, and the operator is always written in terms of the momentum and the position. So this is what you have to do. Do not think that quantum mechanics is very different from classical mechanics. It is the machinery that is different. What you do with it, that is different. The expressions remain the same. The kinetic energy that you learnt about in school is the same as the kinetic energy that you use in quantum mechanics, but you use it differently using operators. Now, what is this is the measurement postulate, because we said that every observable quantity is represented by an operator. I am trying to explain the way you should learn quantum mechanics, so that you are, you don't think that it is just a mathematical subject. You learn how to interpret whatever you are getting from quantum mechanics. It implies that certain properties can only achieve a discrete set of measured values. We will talk about this just now. It is probabilistic. Since you are talking about a wave function, means that measurement can be probabilistic. You can only talk about, you cannot say that position is certainly here. You can only talk about the probability. Measurement necessarily alters the observed system. When you first learned the Heisenberg uncertainty principle, I think in physics NCERT books, it says that, you see what it says is, since you are operating with something, it says that, please show the next slide. I will again show you what is the difference between a classical elephant and a quantum elephant. What it is showing is that when you studied in physics, you must have learned that suppose you are looking at an electron, you will use a microscope. A microscope will use some radiation. The moment you apply radiation, it will gain some energy, a kinetic energy. So its momentum will change. If you determine its position, the momentum is uncertain. That is why you have the Heisenberg uncertainty principle. Now this postulate itself is telling us that suppose you make a measurement, there is an operator there which you apply on the wave function. Wave function is not exact everywhere. You can only talk in terms of probabilities. That means you can only talk about probabilities of measurement. What it says is that suppose you have a classical elephant and you want to find out its position. Before measurement it has some position, after measurement it remains the same, because your eyes are seeing it. You give a very little amount of energy, its energy does not change. It is a huge elephant, nothing happens. So you can determine that this is the position. But suppose you take a quantum elephant which can exist in two states. Remember, it can also be multicolored, rainbow colored, and can also be grey. In that case, if you apply energy, either you can get either the rainbow colored or you can get the position of the grey colored. So you don't know what you are going to get, it is probability. So this is the difference between quantum mechanics. And what else? That before measurement and after measurement, you are not changing the energy of the elephant, because the amount of energy, the visible radiation that you are applying to see this elephant is too small for such a huge elephant, nothing happens. But if you do that for a quantum elephant, the moment you apply any energy, because it has very small size, the measurement changes the state of the system. It can either, it was first a mixture of the rainbow and the grey one, now it can either be just the grey one, or it can either be the other one. See, this is the strange thing in quantum mechanics, that remember some of the experiments, whatever experiment you want to do. Why I gave the cat analogy was that, see, the wave function, when you talk in quantum mechanics, you say these are the probable kinds of states it can be. It can either be in this state or that state, and your wave function will be a sum of all these states, a linear combination of all these states. But when you make a measurement, you will see only one of these states, you will not see all of these states, and this is where quantum mechanics is different from classical mechanics. Classical mechanics, only one state is possible and you see it. Quantum mechanics tells you what are the different kinds of states which are present, and which one of those is, out of these, one of the is the one that you will see. Again, suppose this is an elephant, you can say that its position is here, where it is there, its color is grey, you can say its size is large, you can say all these things. You can say that the position is certain, it is here, it can only exist here, and then it is independent of the measurement, you need not make a measurement, wherever it is there only, and it is only that you see, the observer sees where its position is, and you can write down the coordinates also where it is, the latitude, longitude, whatever you want to write. But when you have a quantum elephant, everything is uncertain until you make a measurement, and while making the position is an action performed on an object which produces some particular result. Any one of the possible states can emerge out of this. In other words, properties like position or momentum do not exist independent of measurement, because if you try to find out its position, the energy that you use, the wavelength, the radiation that you use to do that will alter the energy of that system, and once the energy system, remember that the kinetic energy and momentum are interrelated, its momentum changes. So you have the Heisenberg uncertainty principle. This is a very simplistic way of looking at it, but once we are, I intend to do the particle in a box problem very fully, because it's my belief that if you understand the problem, you can understand the hydrogen atom, you can understand everything. Coming to fourth postulate, the eigenvalues of a linear Hermitian operator give the possible results that can be obtained when the corresponding physical quantity is measured. Suppose you have an operator A and it operates on a wave function which I am calling phi n. It is one of the possible states of a particle. It gives you a constant lambda n multiplied by phi n. What I will define the quantities. A has a hat over it, that means that it is an operator. Phi n is a wave function. We call it an eigenfunction when you operate with A on phi n, you get a constant multiplied by the wave function back again. You regenerate that wave function multiplied by a constant quantity which is lambda n. Now lambda, the nth value, is given, it is called the eigenvalue, and phi is the eigenfunction because you have got it back. A classical example is the exponential function. When you operate with d by dx on exponential alpha x, you get alpha multiplied by e alpha x. So e alpha, I will say it like this: exponential alpha x is an eigenfunction of the d by dx operator, because it gives you back e raised to the power of alpha x multiplied by alpha, which is a constant, and alpha is the eigenvalue. What the third or the fourth postulate says is that if you have a particle in this state phi n, which is an eigenfunction, you can be certain when you make the corresponding measurement of the observable, you will get the same value lambda n. Now I am not talking about probability, it is a certainty. When you are able to find an eigenfunction of an operator given an eigenvalue, this eigenvalue is the value that you will observe every time you make a measurement. I will not use the word time actually. If you have a set of identical systems which exist in this particular eigenfunction, then you make a measurement in any one of these quantities, any one of these wave functions, you will always get the same value specified by lambda n. So this is one of the very important things. Now I am not talking about probability, I am certain that this is a value. The eigenvalues of a Hermitian operator are real, like the eigenvalues of a Hermitian matrix. Remember, at the same time there were two people working on quantum mechanics. There was Dirac, who was working using matrices, and using differential operators was Schrodinger, but we still follow more Schrodinger than the other.
Sorry to interrupt you again, ma'am. We have another caller. Hello. This call is from UP. Hello.
Hello.
Yes. एटम के बारे में जानना चाहते हैं.
जी हाँ.
He wants to know about atom.
ऐसा है कि कल भी एक क्वेश्चन था एटम के बारे में, और मैं एटम के बारे में दिखाने के लिए कि व्हाट इज वेव फंक्शन और वो सब मैं स्लाइड्स देना चाहती हूँ, पर मैं थोड़ा सा लेट मी एक्सप्लेन दिस. जब तक ये नहीं समझ आएगी तो मतलब वो सब आपको समझ नहीं आ पाएगा, इसलिए मैंने आज के लेक्चर के एंड में, और अगर आज नहीं खत्म होता कल के लेक्चर में, मैं आपको दिखाऊंगी कि कैसे आपको ऑर्बिटल्स की शेप पता चलती है, एटम की शेप पता चलती है, क्योंकि एटम का अगर ओनली वन हाइड्रोजन एटम ही सॉल्व हो सकता है, लेकिन हाइड्रोजन एटम को भी सॉल्व करने के लिए आपको स्पेशल फंक्शंस वगैरह की ज़रूरत है. हम सॉल्व नहीं करेंगे, हम जो सॉल्यूशंस हैं उनको डिस्कस करेंगे. ठीक है.
होप द कॉलर माइट हैव गॉट हिज आंसर एंड वेरी सून, दैट इज टुमारो. कल आप बिल्कुल देख सकते हैं कि और जान सकते हैं एटम्स के बारे में, समझ सकते हैं इस मैकेनिक्स के जरिए, इस लेक्चर के जरिए. जी मैम.
So, if you are looking for the eigenvalues of the momentum, eigenvalues and eigenfunctions of the momentum operator, what will you do? You will take the px operator, apply it on some phi p. P we have written that they are eigenfunctions of the momentum operator, and we want a particular value p, an eigenvalue, multiplied by phi px, because you want the wave function back again. See, I am again repeating, this is what quantum mechanics does, that you look for a wave function which is an eigenfunction of a particular operator, because once you get an eigenvalue equation, this is the equation, when you get a constant multiplied by the wave function back again, that this constant is the value that you will measure. See, this is a postulate that is connecting experiment with theory. Theoretically you are doing all this, and what this postulate is saying, that if it is in this particular wave function, then this is its momentum, and you measure the momentum. Hydrogen atom, I think all of you are curious about hydrogen atom, in atoms in general. So hydrogen atom, the energy that you get is the exact energy. There is minus 13.6 electron volt, because this is a problem that is solved exactly by quantum mechanics. The energy that you get for a 1s orbital, minus 13.6 electron volt, is an exact energy. Experimentally, if you can measure the energy, it will turn out to be exactly minus 13.6 electron volt. So this is what we are trying to do. We put in the operator minus iota h cross d by dx phi p x, and we want to get a constant p phi p x. So phi p x can be, you know that for d by dx the eigenvalues are exponential functions, and you will find that it has to be an imaginary number. Iota you have to multiply kx to get this, so that p is equal to k h cross from the de Broglie relation. And remember that I told you that for the momentum the units are h cross. Momentum in quantum mechanics will always be in units of h cross, and h, if you remember, is just 10 raised to the power of minus 34. So h cross is even smaller, and the momentum values are extremely small. So when you have this operator minus iota h cross d by dx, the momentum operator, when it operates on the eigenfunction exponential iota kx, it gives you kh cross into exponential iota kx, and I can say that the measured value of the momentum will turn out to be kh cross. In units of h cross, it is equal to k. We also talk about the complete set of functions. Suppose now in quantum mechanics, whatever little you've learned about the atoms, you know that you'll come across some quantum numbers, some discrete values. You'll say that n can only take on 1, 2, 3 values, but not values like 1.05 or anything. Nothing between 1 and 2, either 1 or 2 or 3, any integer value, something like that. So you will get the corresponding eigenfunctions also corresponding to different values of n. Depending upon your system, n can take on 0, 1, 2, 3 values or 1, 2, 3. That depends upon the system. What it says, I think what it says is that you can always expand your function in terms of these eigenvalues. Coming to the second portion of this postulate, when a measurement of the observable q is made on a normalized function psi, the probability of obtaining the eigenvalue CR is given by the modulus squared of the integral. I'll say it in simple words. We talked about in the last postulate, we said that if the system is in an eigenfunction of, if it is represented by a wave function which is an eigenfunction of the operator for which you are looking for the experimental value, then every measurement that you make of that particular quantity, you will get only the eigenvalue. You will only make that measurement. This postulate says that suppose it is not in an eigenfunction. In that case, you will get one of the eigenvalues, but with a probability that is given by the square of the, after you made a use the complete set to write it in terms of those. So the square of the modulus will tell you the probability. All I want to say is that you can talk about the mean value then. All this postulate tells you is that you'll get different values corresponding to the eigenvalues, but the mean value can be predicted using this theorem. This is called the expectation value, where to find out the expectation value of q, look at the second equation, you write down the wave function, the complex conjugate, you operate on the wave function by q and then integrate it over all space. This tells you about the expectation value, which is actually the mean value. I'll repeat what the last two postulates said. They said that if the system is in an eigen function, if it is represented by a wave function which is an eigen function of the operator that you are looking at, in that case every time you make a measurement of the observable corresponding to that operator, the same value will be obtained. There is no uncertainty. I can prove that, but I will not prove that, just take it as a postulate that it will give you the same value. The second one says is, suppose you are not able to find an eigen function, because the aim of all quantum mechanics is to find out eigen functions of the energy, the Hamiltonian operator, so that you can find out the exact energy. But sometimes you are not able to do that. It says that in that case you will get different values, but all the values that you measure are the expectation values, but the eigenvalues, but the expectation value is given this, and by the second equation that I have shown, that is, you insert that operator between the wave function and its complex conjugate, operate with the operator on that function, multiply by psi square, and then you integrate over all space. This is the expectation value or the average value. It is something like psi star, psi, you remember, is the probability. Suppose there are 10 students in a class and they have got different marks. How do you find out their marks, the average marks? If 3 students have got 5 marks and 2 have got 4 marks and so on, the probability of a particular mark depends upon how many students have got. So if there were 10 students, 3 got 5 marks, you say that the probability of 5 marks is 0.3, 3 divided by 10. Same thing here, the probability here is psi star into psi, and you multiply by the operator, here you multiply by the marks. So you multiply 0.3 by 5 and 0.4 by 6 or whatever are the marks, and you get the probability.
Yes, ma'am, we have very less time left, and I would only say all those callers who have called us, thank you so very much. I hope you all have got your answers, and tomorrow also Professor Kakkad is going to be with us in our EduSet lecture, and we are going to discuss more about quantum mechanics. Thank you so very much, ma'am, for being with us.